Today we're talking about states of matter, and here we've got, California, Texas, and Florida, but we're talking about a different meaning of the word states today. Okay, so there are 4 states of matter that occur naturally in the universe. There's solids, liquids, gases, and plasma. And then there is one 5th state of matter that we've made in a lab, but we haven't seen it anywhere else occurring naturally. They think it could possibly exist inside of black holes, but we're not sure. So these are the main 4. There's 3 main factors that have a big effect on what state of matter the substance you're looking at is going to be in. So it's the arrangement of the particles, how tightly they're packed, or what kind of pattern they're taking, the energy of the particles, and another, in science and in chemistry, energy and heat are interchangeable. They mean the same thing pretty much. So the energy of the particles is just kind of another way of saying how much heat they have, what temperature your substance is, and then the distance between the particles. So whether they're close together or spread apart, all 3 of these things have a big impact on what state of matter your substance is going to be in. And when you have those 3 factors all working together, they all contribute to what's called the kinetic theory of matter. So what that means in a vague sense, the big picture, is that everything, all matter, is made up of tons and tons of tiny little particles which are in constant random motion. So you can see here you've got a bunch of different little particles that are all just kind of moving around, bouncing off each other randomly. Okay, when you have a solid, so this is our first state of matter that we're going to talk about. Let me move myself back down to the corner here. When you have a solid, the particles in the solid are all very tightly packed together. All right, they're so tightly packed that they can't move past each other. They're kind of stuck in one spot, but they are still all moving. They're vibrating back and forth. All right, they just can't slide past each other and move around, really. All right, solids, as a rule, have a definite shape and a definite volume. Okay, so like my phone here, it's not going to suddenly melt and fall out of my hand and change its shape, or grow larger or shrink smaller and change its volume, right? It's a solid. It is this shape and this size, and that's not going to change. Okay, liquids, so the particles are still pretty tightly packed together, but they're just spread apart enough. I don't know if y'all can see here. Let me move myself out of the way. They are just spread apart enough to where they can move past each other and slide over one another. All right, they have a definite volume, so 30 milliliters of water is always going to be 30 milliliters of water. It's not going to suddenly expand and take up 60 milliliters. But not a definite shape, which is why when you pour a liquid into a container, it takes the shape of that container. All right, and then gases. The particles in gases are very far apart generally, and they move around all over the place very quickly, bouncing off each other, bouncing off the walls of whatever container they're in. They don't have a definite volume, which means that whatever amount of gas you put into a container, it's going to spread itself out as thin as it needs to fill up that container. Which means, like I said, they're going to expand to fill whatever container they're put in and take the shape and the volume of that container. This is also why gases are compressible. We talk about like aerosol cans or CO2 cartridges, scuba tanks, everything like that. the reason you can compress gases down like that and store a bunch of them under high pressure in relatively small containers is because their particles are so far apart, there's all that empty space between them that they can all be kind of squished down into. Alright, there's different names for when solids and liquids and gases and the different states of matter change in between one another. So if you're going from a solid to a liquid, it's melting. You guys have all, I mean, these ones are pretty self-explanatory, right? If you have ice and it turns into water, solid to liquid, it's melting. If you have a liquid going to a solid, so water going to ice, freezing. Duh. Alright, these other ones, maybe you've heard of, maybe you haven't. If you're going from a liquid to a gas, so you're boiling water, or water is sitting out in the sun evaporating, we call that vaporization as our broader term, right? It includes both boiling and evaporation. And if you're going from a gas back to a liquid, it's called condensation. So anytime you're switching between phase changes, make sure you remember what name of the transition, what the term is for it. Okay, and then these last two, there are some substances, some chemicals that don't have a liquid phase at all. They go straight from being a solid to being a gas, and straight from being a gas back to being a solid when they're cooled down. So the most common example of this that you guys might know of is dry ice, which is solid carbon dioxide. And when it goes from being a solid and gets warm enough that it's not a solid anymore, it doesn't melt, it turns straight into a gas, and that's called sublimation. Right? And when it goes the other direction, when they cool it down to make the dry ice, going from a gas directly to a solid without going through liquid first is called deposition. So those are the two tricky ones that you might not have heard before, so keep that in mind. Okay, at the beginning, I did say that there were 4 phases of matter, and we've only talked about 3. The fourth one is plasma. So plasma is not super common here on Earth. It does occur, but out in space, out in the cosmos, it is the most common state of matter. Alright, a plasma is basically just a gas that is very energetic. So it has so much energy in it that every single particle has an electric charge. They're what's called ionized particles. And it responds to magnetic fields and electric fields around it. I keep clicking the wrong thing. There we go. Like gases, they don't have a definite shape or volume. So they'll expand and fill up whatever container you put them in. So here, these videos aren't working, are they? Well, here, one example of plasma on Earth is in neon lights. The neon gas in there that we run the electric charge through to make it glow like that. Once the electric charge is running through it, all those particles are ionized, so it is a plasma. And what this video is supposed to show, let me see if I can get it to play. I guess it only came in as a picture. That's a bummer. I'll fix it and put these 2 videos in along with mine so you guys can watch them. But what this video was supposed to show was this plasma in the neon tube reacting to the magnetic field of the magnet, if you watch carefully. Alright, and then another example of plasma on Earth is the Northern Lights, or Aurora Borealis is the other name for it. And that's when plasma in the Earth's atmosphere reacts with the Earth's magnetic field to make these really pretty lights in the sky when you're in northern latitudes. So, some examples of plasma on Earth. The 5th one that I said was only present in labs or possibly in the center of black holes is what's called a Bose-Einstein condensate. And this is the state of matter. So where plasma was a very, very energetic state of matter, the particles were moving around very quickly and they were all ionized. Bose-Einstein condensate is at the opposite end of the spectrum. All right, this is a state of matter with very, very little energy in it. It only occurs at or very near absolute zero, which means that absolute zero is the coldest anything can possibly get, which means that the particles in this are not moving at all, hardly. They're moving very, very, very slowly, and all of the particles move together in the same direction at once, rather than bouncing off of each other like they would in a solid. It was predicted to exist by Albert Einstein in 1928, but it took almost 70 years for someone to actually be able to create it and prove that it existed in a lab. Alright, so that is states of matter. You guys have a quick 10 questions homework assignment about this. And if you have any questions, let me know.